All right, guys, we have made it to the end of polynomials. We are now just looking one last time at graphs of polynomials. Today, we're going to focus mostly on the degree of our function and its in behavior, as well as the multiplicities of our graph as it approaches our x-axis. So that's going to be kind of the last part that we'll look at, comparing our equations to our graphs, and then we're going to be done with this unit. All right, so as a warm-up, for each of our graphs, or for each of our functions below, we're going to state the in behavior without graphing it. So we're going to have to use some of that information that we talked about at the end of 5.7 to be able to work through these. Now, obviously, for our quadratics, those are pretty easy to remember. If it's positive x squared, then it's opening up. That means that as our x values go towards negative infinity, our y values go towards positive infinity in both directions. So again, f of x is really just saying the same thing as y, and x going towards negative infinity. Don't worry too much about that limit notation. So really, you just need to write what y is going towards. Which makes it pretty easy, because on f of x is equal to negative x squared, then we've got a graph that opens down. That means that on both directions, our y values go towards negative infinity. Now, even though we're not as familiar with x cubed, it's kind of the same in behavior-wise, so the same in behavior as f of x just equals regular old x. In other words, we've got a graph that's got the same in behavior as just a normal line, in which case, on the left side, you're going down towards negative infinity, and on the right side, up towards positive infinity. Which means on D, then we're going to have the same in behavior as f of x equals negative x. So when you think about negative x, that would be your line pointing in this direction instead, which means that on the left side, you're actually pointing up towards positive infinity, and on the right side, you're pointing down towards negative infinity. So let's now kind of talk about how you can tell what the degree of a function is by looking at its graph. So keep in mind, as we work through these, we're talking about the degree for our polynomial. We're also going to talk about whether it's a positive or negative leading coefficient. Basically, what we're going to do for each of these problems is we're going to compare what it looks like to either a linear function or a quadratic. So to show you what I mean, on example A, if we were to try to match this up with a quadratic, it would match in one direction, but not both. But instead, if maybe we used a linear function, so a straight line, then we could draw a line which had the same in behavior as our function. Since it's got a line, remember lines like y equals x have a degree of 1, that tells us that this function is an odd degree. Now, remember back in Unit 1 we talked about even and odd functions. Odd degree does not mean that it's an odd function. It just means that the degree of our polynomial is odd, either 1 or 3 or 5, but it doesn't necessarily mean that it's an odd function. So, for the first part, we'll say that it's an odd degree. Now, the second part is that really this line that we graphed would not be y equals positive x, because notice that it's going down. So this would be y equals negative x, would be a closer comparison. In other words, our leading coefficient, which I'll just abbreviate LC, would have to be a negative number. That's a lot of information to get just by looking at the graph about what our equation would look like. Let's go ahead and do the same thing with B. So with B, obviously we can't do the same thing. We're not going to be able to use a linear function. It's only going to match in one direction, but not both. So instead of using a linear function, let's try to use a quadratic function. And if we were to draw a quadratic, we would be able to draw one that used the same in behavior as our current function. And if that's the case, then really what we want to compare this graph to is y equals x squared, and in which case our degree is going to be an even degree. Now again, that does not mean the same thing as even function, it just means that it has an even degree. And if you look at our graph, obviously our quadratic is opening up, which means that our leading coefficient would have to be positive. So the leading coefficient for our current graph, which has more of a U shape, or W shape, which is probably going to be quartic. We also know that the leading coefficient is going to be positive for that function as well. All right, let's go and do C. So for our degree, obviously a line is going to be a better fit. Notice that if you draw a line, you'll get the same end behavior as your current function. So that tells you that this is going to be an odd degree. And for the slope of that line, we have a positive slope. That tells us that the leading coefficient is going to have to be positive. For our last graph, pretty clearly, we could draw a quadratic that matches. In fact, this is most likely a quadratic itself. That clearly tells us that this is even degree. And if it's even degree, opening down, that means that our leading coefficient is going to have to be negative. So when you want to know what the degree is, compare it to either a quadratic or a linear equation. If it follows a linear equation better, like A and C did, then we know that it's going to be an odd degree. If the end behavior follows a quadratic better, like B and D did, then we know it's going to have to be even. Then if it's an odd degree, look at the slope of the line. If it's a negative slope, a negative leading coefficient, positive slope, positive leading coefficient. For your even function, or for your even degree polynomials, then look to see if it's opening up or down. If it opens up like it did in B, that's going to be a positive leading coefficient. If it opens down like it did in D, that's going to be a negative leading coefficient. Okay. For A and B on this next part, we're going to kind of skip over them. Really, all I needed you to know about transformations is that they don't necessarily work. In fact, it's kind of unfortunate. Only our polynomials of degree 1 and 2, so our linear and our quadratic polynomials, have true parent functions. If you get to polynomials of 3 and larger, so cubic and up, so quartic and quintic, they don't actually have a true parent function because some of the graphs will look different than the parent function does of f of x equals x to the fourth. So we really don't talk too much about parent functions. That's kind of what that section talks about. If you want to see that, go back and graph your two sets of equations. What you're going to see is that for A, the shape of your graph stays the same, whereas for B, the shape of your graph becomes noticeably different. So just wanted to mention that to you as far as those graphs go. All right. So let's talk a little bit more about multiplicities, because we've talked a little bit about them, but we haven't necessarily defined them in any sort of the sense. So when we talk about multiplicities, an even multiplicity is going to bounce off your x-axis. These are the ones that we've seen before. These are the ones where they actually change direction. An odd multiplicity instead simply passes through the x-axis, so you're not going to have that same change in direction. So when we're looking at each of these graphs, we're going to first decide what type of multiplicity is it, even or odd, at our x value of 1. So for the first graph, at x equals 1, pretty clearly our graph does not bounce off the axis, but passes through. In fact, it almost looks like it was going to change directions, but didn't. When that happens, we're going to say that that's an odd multiplicity. So for number 2, again, looking at where x is equal to 1, that definitely does bounce, so that's going to be an even multiplicity. Finally, for our third graph at x equals 1, once again, you have a graph that looked like it could have changed directions going in either direction. In this case, it did not change direction. That would be an odd multiplicity, which really does help us to describe behavior of a graph by looking at their factored form. So for example, on number 4 here, if you're looking at your equation, you're going to end up with two zeros. You're going to have x equals positive 2 and x equals negative 1. Now, one of those is happening multiple times. If you notice, the factor of x minus 2 is happening twice. So that means that at x equals 2, we have a multiplicity of 2, which is an even multiplicity. So the behavior is that it's going to bounce at that value of 2. So if you were to look at the graph of this function and look at x equals 2, you're going to see that your function bounces at that point. For number 5, we actually have two zeros with multiplicities. We have the 0 of x equals 1 and a second 0 at x equals negative 5. Let's start by taking a look at this 0 at positive 1. So that would be at x equals positive 1. The multiplicity, look at your exponent, is happening 3 times. That is an odd multiplicity. So the behavior is that it's going to pass through.
On Monday, February 8th, at 2:45 p.m.
Sorry for the announcements. Hopefully you'll be able to still hear this. All right, the second one was that x equals -5.
Thank you.
The multiplicity at that is the number 4, so it's happening 4 times, so that is an even multiplicity. So the behavior for that one is that it bounces when it gets to the x-axis. Finally, for our last one, for number 6 here, we do still have 2 zeros at -3 and -7, but notice that there are not any exponents attached to the parentheses, so there are no multiplicities. All right, guys, that is all we've got for this section. In fact, that's all we've got for this unit. We've made it to the end of Unit 6, or Unit 5. So that being said, we will be starting a project very soon where we're going to use this information that we've learned, in particular about the graphs of our polynomial functions, in order to describe a roller coaster of some kind. That being said, until next time, have a great rest of your day.